In September 2024, a massive landslide struck the Rancho Palos Verdes area of California, forcing local authorities to declare a state of emergency. This landslide, primarily affecting the Portuguese Bend region, caused significant damage to homes, roads, and utilities. The land continued shifting with alarming speed, moving as much as 1 foot per week, prompting evacuations and immediate response from both state and federal agencies. From an engineering standpoint, the Rancho Palos Verdes landslide is a textbook example of how complex and unpredictable the forces of nature can be, particularly in areas prone to geological instability. In this update, we'll dive into the key engineering concepts and strategies used to monitor, stabilize, and prevent further damage from this major landslide event. Before we continue, I'd really appreciate it if you could hit that subscribe button. I'm working towards 1,000 subscribers, and your support would mean the world. Don't forget to like and comment. It really helps out the channel. Understanding why this landslide occurred begins with looking at the soil composition of the region. The Portuguese Bend area is composed largely of clayey soils, which, while abundant, are particularly vulnerable to slippage when they absorb excess moisture. Clay has low cohesion, which means it doesn't hold together well when it gets saturated, especially after heavy rains or seismic events. In this case, the winter rains of 2024 created the perfect conditions for instability. The moisture weakened the soil's structure, causing it to lose its grip and slip downhill. What's particularly dangerous about the area is its history. Portuguese Bend has been experiencing slow, persistent land movement for over 7 decades. It's a reminder of how certain landscapes, with the right conditions, can remain active landslide zones for long periods of time. Once the landslide began to progress, it was crucial for engineers to monitor how fast and where the ground was moving. Advanced monitoring systems came into play to track the shift and understand its behavior in real time. Engineers typically use inclinometers, which measure the angle of slope movement, and tilt sensors to track the slightest changes in the ground's position. GPS systems are also invaluable, using satellite technology to give precise measurements of displacement. These tools provide engineers with critical data on the movement of the landslide and allow them to predict where the land might shift next. At Rancho Palos Verdes, the rate of movement was measured at up to 1 foot per week in certain sections, which raised significant concerns about the safety of homes and infrastructure in the area. This rapid movement meant that quick action was needed to stabilize the situation before further destruction occurred. When a landslide moves with such force, the first priority is to contain the immediate threat, to stop the movement and prevent further damage. This requires a combination of temporary and immediate stabilization efforts. Engineers rely on several methods to halt or slow down the landslide before long-term solutions can be put in place. Retaining walls. Holding the line. One of the first things engineers will often deploy in landslide-prone areas is retaining walls. These engineered barriers are designed to resist the pressure exerted by shifting soil. Constructed from materials such as concrete, steel, or geosynthetic fabrics, retaining walls essentially act as stopping points for the landslide, preventing the earth from continuing its downward movement. In Rancho Palos Verdes, retaining walls were placed at high-risk sections along the landslide path to reduce the risk of homes being engulfed. Soil nailing, locking the soil in place. Alongside retaining walls, soil nailing is another technique used to stabilize shifting land. This involves inserting steel bars, called nails, into the unstable soil at an angle. These nails are then grouted into place, essentially locking the soil to its new position. This method is particularly effective in areas where the land is moving slowly but steadily, as it helps anchor the soil and prevent further movement. Monitoring and warning systems, real-time insights. The ability to monitor landslides as they happen is one of the biggest advancements in engineering. Real-time monitoring systems can detect even the slightest shifts in the land and provide immediate feedback. For example, piezometers, which measure water pressure in the soil, allow engineers to understand how moisture levels are affecting soil stability. This type of system is essential for assessing the risk of future shifts, ensuring that engineers can make adjustments to their efforts if the land begins to move more rapidly. While short-term measures are crucial in stabilizing the area temporarily, The true challenge lies in preventing further landslides and mitigating the underlying causes of instability in the long run. Engineering solutions to this problem need to address not just the immediate damage, but the long-term risks associated with living in a landslide-prone zone. Regrading and slope reshaping, reducing the steepness. One of the most effective ways to prevent future landslides is to regrade the slopes. This involves reshaping the land by redistributing the soil to reduce its steepness. Steeper slopes have higher potential for landslides, so by gradually flattening the terrain, engineers reduce the forces acting on the soil, making it less likely to slip. Regrading might involve excavating sections of the slope or terracing, where steps are built into the land to help redistribute the weight. Drainage management controlling water flow. Water is both a cause and a solution when it comes to landslides. Excess moisture in the soil weakens its structure, while properly managing water flow can greatly reduce the risk of instability. To combat this, engineers have designed advanced drainage systems that will carry water away from critical areas. French drains, subsurface drainage systems, and surface runoff channels all work together to manage both groundwater and surface water, preventing the soil from becoming overly saturated and reducing the likelihood of further shifting. Geotechnical drilling digging deeper into the problem. Understanding the exact causes of the landslide requires geotechnical drilling. By drilling deep into the earth, engineers can extract soil and rock samples that reveal important information about the land's structure. This allows for a better understanding of the soil's strength, the depth of the bedrock, and how much water is present in the soil. Armed with this data, engineers can design more targeted stabilization methods and predict how the land will behave in the future. To support residents in the affected area, the state of California introduced a $42 million buyout program. This program offers residents the option to relocate, with compensation based on the pre-disaster value of their homes. From an engineering standpoint, this is a smart strategy. It removes people from the highest risk zones, helping to prevent future disasters. However, it also opens up questions about land use planning in regions like Rancho Palos Verdes, where the risk of landslides may always be present. Future development in these areas will need to take into account the lessons learned from this event. The Rancho Palos Verdes landslide is a vivid reminder of the importance of understanding the geological forces at work in unstable regions. It also underscores the need for advanced monitoring systems and proactive engineering strategies to deal with natural disasters. From retaining walls to drainage management and geotechnical drilling, engineers are using every tool at their disposal to prevent further damage and ensure the long-term stability of the land. As we move forward, it's crucial to invest in better land use planning, early warning systems, and comprehensive geotechnical research to help mitigate the impact of landslides in vulnerable regions. With the right engineering solutions and forward-thinking strategies, we can reduce the risks posed by such disasters and protect communities for years to come.